Alright kiddos, welcome back. And today we are going to talk about hybridization, try to wrap up our unit on bonding. Now, in order to theoretically justify the VSEPR model, remember the valence shell electron pair repulsion model, some adjustments need to be made in the electron arrangement of bonded atoms. Let's consider a Lewis structure that we've drawn several times now, CH4. If we write the configuration and orbital diagram for a carbon atom, if you remember, we end up with this: 1s2, 2s2, 2p, and let's just check our periodic table again. Looks like it's 2 into the 2p, so 2p2. The orbital diagram, and let's just worry about the valence electrons, folks, would be my 2s sublevel with 2 electrons, and my 2p sublevel with also 2 electrons, but they're in separate orbitals. Now, look at the orbital diagram here, this guy right there. How many bonds should carbon be able to make? Remember, a bond is a shared pair. So if carbon's going to share a pair, can it share one in the 2s? No. Could it share one there? Sure it could. That would be a shared pair if another electron came in and shared that orbital. And it could also share one right there. So we would think, well, maybe it could make 2 bonds, right? It could make, it could have 2 shared pair. But obviously, in CH4 methane, how many bonds is carbon really able to make? Well, it can make 4. So how do we explain this? How do we explain that it can actually share 4 pair when if we draw the orbital diagram, it looks like it can only share 2 pair? Well, the answer is the process known as hybrid orbitals. Hybrid orbitals are orbitals formed from the mixing of orbitals of different energies. For methane, it goes like this. So let's take a look at this picture here. Here's the orbital diagram, 2s2, 2p2, that's just what we saw above. What if this s electron, one of these s electrons, gains a bit of energy and is promoted to a p sublevel? Then wouldn't we end with an s1 and a p3? And we would say, okay, Hummer, it looks like now we can share 4 pair. But don't forget, the s orbital is a spherical orbital, and the p orbital has this figure 8 orbital. How would those 2 orbitals account for, actually 4 orbitals, how would they account for the 109.5 degree bond angle that we see in methane? Well, the way we understand it, or our theory is that this s orbital and these p orbitals hybridize, they merge, and they form what we call a hybrid orbital, which has characteristics of both. It has a little bit of s characteristic to it and a bunch of p characteristic to it. So we call this an sp hybrid orbital. Now, if the s hybridizes with one p orbital, we call it an sp hybrid. If it hybridizes with 2, we call it an sp2 hybrid. If it hybridizes with all 3 p orbitals, we call it sp3. So we can have sp, sp2, or sp3. In the case of methane, we end up with the s hybridizing with all 3 p orbitals, so we call it sp3 hybridization. So if we have 4 of these sp3 hybrids, and they're all coming out of, let's change colors here, they're all associated with that central carbon atom, we would have 1 electron in each of these orbitals, and they would be as far away from each other as possible, wouldn't they? And we would end up with this characteristic tetrahedral shape. Now, if there were 1 electron in each of those orbitals, let's make those yellow, an electron, an electron, an electron, an electron. So 1 electron made up each of those orbitals. Can't I make 4 bonds? Can't hydrogen come along? So let's say here's a hydrogen atom. And remember, hydrogen's electron configuration is 1s1, so it just has that s orbital. We can put another hydrogen here with its s orbital, and another hydrogen here with its s orbital, and then up here with its s orbital. And let's go ahead and show its 1 electron. Can't a pair be shared there? and a pair be shared here, and a pair here, and a pair here. So we end up with 4 shared pairs, and we end up with this CH4 molecule, which has a tetrahedral shape and a bond angle of 109.5. Okay, let's try to do the same thing for ammonia, NH3, and water. The simple p orbital model does not account for the observed bond angles of just under 109.5 for either of these. So here is the unhybridized model. So let's take ammonia first. We're going to take the central atom nitrogen in ammonia. Let me switch colors here because this is a blue illustration. So nitrogen, of course, has the electron configuration 1s2, 2s2, 2p3. And if we don't hybridize those orbitals and we look at just the valence electrons, we have a pair in the 2s and we have 3 electrons in the 2p. So you'd say, okay, that's cool, Hummer, because now those p orbitals each can share another electron, and we could have 3 shared pairs. It can make 3 bonds, Hummer, and that's what ammonia has. After all, isn't it NH3? Well, we have an issue with that, remember. Remember, the s orbital is a sphere, and each of these p orbitals has that figure 8 shape to it. So it wouldn't account for the bond angle that we see in ammonia. That is right around 107 degrees. We couldn't end up with this structure, this trigonal pyramidal structure either, if we had this s and p orbital configuration. So once again, it's believed that they hybridize or they blend together, and we end up with this sp hybrid. Now we still have the s hybridizing with all 3 p's, so we're going to end up with sp3 hybrid orbitals, which we see right there. Now when you look at this, do you notice that that orbital right there can't share a pair? It's already full. But we can have an electron in this orbital, and this orbital, and that's exactly what happens with the hydrogen atoms. Can you see them right over here? Right there, the s orbital of hydrogen has its electron, and it's sharing an electron with one of those sp3 hybridized orbitals from nitrogen. Same thing happens here, and the same thing happens here. And then notice in this orbital right up here at the top, it's illustrated right here on the top, kiddos, notice it's a non-bonding pair. Both of those electrons come from nitrogen. They're not shared between nitrogen and hydrogen. All right, let's take water. So now let's take a look at the water molecule here. Let's switch to, I don't know, we'll use this bright color here. So let's look at H2O. If we look at oxygen's configuration, it's 1s2, 2s2, 2p4. And the non-hybridized orbital diagram, we'd have the 2s2 and the 2p4. Notice that these 2 orbitals here and here are full. And so these orbitals here and here could make a bond. But remember, those are p orbitals, which have that figure 8 shape, and it wouldn't account for this bond angle here, which is around 105 degrees, and it wouldn't give us the bent shape that we see in the water molecule. So once again, what we believe happens is the s orbital combines with the 3 p orbitals, and we end up with this sp3 hybridized orbital. So we have 4 of them. 2 of these, though, can't make a bond. They're already full, kiddos. However, these 2 can make a bond. And they would be about 109.5 degrees from each other if it were a perfect tetrahedron with all 4 of those orbitals. But remember, these 2 orbitals here take up more space because they're not being shared between nuclei, so it reduces that angle to about 109.5. Now, the secret to this, kiddos, is simply looking at the central atom. If we have any atom or any molecule like CH4 or H2O or NH3, and we draw their Lewis structures, and we see 4 regions of electron density. Fit this in here. Around that central atom, that will give us this sp3 hybridization. 4 regions of electron density result in sp3 hybridization. Now, you're asking yourself, well, can there be anything other than sp3 hybridization? Well, yes, there can be. Let's take BF3. Remember, boron was one of the exceptions to our octet rule. We said it only needs 3 pairs around it to be stable. It only makes 3 bonds. So, let's see how that happens. If we were to draw the electron configuration for the boron atom, let's take a look at it on our periodic table. It's right here next to carbon. Wouldn't it be 1s2, 2s2, 2p1? Okay, so 1s2, 2s2, 2p1. So the orbital diagram would look like this. 2s2 for the valence electrons, kiddos. 2p1. And you'd say, well, the boron atom can only make 1 bond. Well, what if one of these s electrons is promoted? And then we would have this type of orbital diagram, and then the s and only 2 p's merge together. You might say, well, how come all 3 don't merge together? Well, because there's nothing over there. So we have an s and 2 p's merging together. Now, if we have an s and p orbitals that merge together, remember, they make this little unique hybrid, or this little unique looking orbital that gives us the characteristic sp hybridization shape. Now, if we have 3 of these, and I'm going to try to draw these for you. Here's one bonded to the boron atom, and the other one will be over here somewhere, and the other one will be over here somewhere. Wouldn't you expect that angle to be 120 degrees? Yeah, that's as far away from each other as they could be. It's no longer going to be 109.5 degrees because we don't have anything in that 4th orbital, kiddos. So we end up with the boron atom in the center with its 3 electrons. 1, 2, 3. So it's 1, 2, 3 electrons. And all 3 have this sp2 hybridization. And then when fluorine comes along and shares an electron with it, we can share here, here, and here, and end up with a nice BF3 molecule that is trigonal, planar, with a 120 degree bond angle. Let's talk about BEF2, another exception, beryllium, to our octet rule. Its electron configuration is 1s2, 2s2. And if we look at the orbital diagram for that valence electron, we end up with these 2 electrons here, and you would say, well, beryllium can't make any bonds at all, Hummer. Well, what if one of these s's is promoted, and then those 2 hybridize to form an sp hybridization? Now, it can't be sp2 or sp3, kiddos, because there aren't any electrons over here. So each one of those orbitals looks like this. We have the beryllium atom in the middle. The other one would come out like this, and we would have, just like we see here, a 180 degree angle between those 2 hybridized orbitals, each with 1 electron in it and available to make a bond. Okay, so to simplify this, if we see 3 regions of electron density around a central atom, we will have sp2 hybridization. And of course, if you see 2 regions of electron density around the central atom, we would have sp hybridization. Now the question might come into your mind, well, Hummer, we've done a little bit with expanded octets in our class, not a whole lot. We will next year in AP. What if there are 5 regions of electron density, or 6 regions of electron density? Well, then we end up with sp3d for my 5 regions, and sp3d2 for 6 regions. Okay? All right, we'll stop there. I want to do a little bit more with this in the next video. I want to talk about something called sigma and pi bonding and further our discussion on hybridization. Thanks. See you in a bit. Bye-bye.